and that we're not going to jump right into homework and stuff. I just want to talk a little bit about magnetic fields because they're very strange. So, which that is what homework 5 is about, but I kind of want to spend the day just getting you used to the idea of them. I was going to do this on Wednesday, but I showed up on Wednesday.
So I wasn't the only one that didn't show up?
You were not the only one who did not show up on Wednesday. So
I was going to, if I had one of the mornings again. It's been like 8:30 when I got here. I didn't figure there was one thing.
Yeah. All right. So magnetic fields. So if you remember back to electric fields, I may just take the tablet straight off of it. Electric field was pretty simple. It's just, okay, the force is charge times E, right? So as far as like direction or whatever, so the direction of E is the direction of positive charge is accelerated. So basically, if you imagine just like, I've been assuming you don't have any initial velocity or whatever, you just take a charge and set it out in the electric field. Well, if it's a positive charge, it's going to follow the electric field. If it's a negative charge, it's going to go opposite, right? So this was very simple to visualize or whatever you kind of think of. The electric field's like a wind, and when you put the charge there, it follows the wind. That is not how magnetic fields work at all, right? So for magnetic fields, the situation's much more, I mean, it's more complicated, but mainly it's just weirder. And I think I have the direction right. I should have probably looked this up before it's either V cross B or it might be B cross V, but I'm pretty sure those are in the right order. So now it's time to go back to the very beginning of Physics 1 and remember everything we learned about cross products. Do you remember everything we learned about cross products?
I hate cross products.
You hate cross products. So
but these are simple cross products, so probably okay.
Yeah. So the first thing to remember about cross products is that the answer is always perpendicular to both of the input vectors. So what that means is that if I have a magnetic field on a charged particle, then the acceleration is always perpendicular to the field and also perpendicular to the velocity of the particle. All right, so just to give you a simple example, let's say we have a magnetic field that's going to the right. I've got a particle that's going up. Let's say it's a positive particle. So remember your right-hand rule. Your right-hand rule says to figure out the direction of a cross product, you put your right hand on the first vector with the palm facing the second one. So if I put my right hand on the V, Let me get out of the chair to do that. So I want my right hand on V with the palm facing V. So right hand is along V, palm is facing V. My thumb is going into the board. So that particle would be accelerated straight into the board. So it don't keep going the same way it's going no matter what. And it does not follow the direction the magnetic field is going. So that's, I'm basically going to say the same thing over and over and over at this point. But I just want you to get that in your head that the magnetic field is not in the same direction as the force. It's always perpendicular. Weird as all get out. But it works. So, all right. Let's do another simple one. So, let me finish reminding you about cross products. So, again, just quick recap for college physics people. Cross products are pretty simple. It's just V cross B. You do the magnitude of V, the magnitude of B, and then sine of the angle between them. So this is, or usually you just drop the arrow, say VB sine theta, as far as the size of it. And then the direction, again, you do that right hand rule. So you put your right hand on V with the palm facing B, and then the thumb is the direction. Okay, so if you're in college physics, that's all you need to know about cross products. So if you're in university physics, you kind of need to know the algebra for them, which do you do just like the simple products, or do you like doing, have you seen the determinant thing, or do you have a preference? Okay. Yeah, so I like the simple one better too. I just remember I times J is K, J times K is I, K times I is J. And then the other thing is if you do anything times itself, you always get 0.
Yep.
And if you swap the order on two of them, you always get a negative if you switch it. So like I times J is K, but J times I would be negative K. So you can just do that and then do the distributive property, or you can set up the matrix thing. It's two ways of writing the same thing, but I think that's simple. So. All right, cool. Well, let's do something simple then. Let's say we got, well, again, let's put a magnetic field going to the right. And by the way, the unit of magnetic field is a T for Tesla. How many of you have heard the name Nikola Tesla at some point in your life?
Oh, I've been around you.
You've been around me enough. He's basically the reason why America became the world's technological superpower at the turn of the century is because this Croatian dude immigrated to the U.S. He had a dream of building a giant water wheel on Niagara Falls and powering the country with it, which sounds kind of silly. But I mean, that's basically what he did.
And the books he read were new his.
I mean, that's the thing, is that he's one of those guys that just loved discovering things. So he had no business sense whatsoever. I mean, he made millionaires out of half a dozen people, but he himself was not very good with money. So, okay. So if we have a field that's 2 Tesla, let's say we got a particle going at a 30-degree angle there, and say the charge is 2 coulombs and it's going at 5 meters per second. Well, what's going to happen to it? Well, first of all, let's get the direction. That's the easy part. If I put my hand on the velocity with my palm towards B, again, my thumb is going into the board. So it's going to accelerate into the board. Okay. Accelerate into the board. What's the force on it? Well, the force is Q VB sine theta. So 2 times 5 times 2 sine of 30, which is a half. So that's 10. 10 newtons. All right. Let's say instead of just being a generic particle, it's, I don't know, let's give it some mass. Let's say this thing is pretty big for a particle. Let's say it's like 10 to the minus 15 kilograms. Proton's like 10 to the minus 19 or something. So, or no, proton's like 10 to the minus 27. So yeah, this is really big. So what would the acceleration be? This is back to first beginning of physics.
Just take the mass multiplied by 8. So, take the mass, or whatever that is.
Yeah.
I don't know.
Okay, what you're trying to say is force is mass times acceleration, right? So F is ma. So what's the acceleration? Well, we know the force is 10 divided by 10 to the minus 15 kilograms. So this thing is going to accelerate at 10 to the 16th meters per second squared. A lot.
Yeah.
Okay. Cool. So you're probably getting the idea, at least I hope you're getting the idea by now, that it's kind of hard to visualize what's going on. Because, okay, you think about this one, it was going off at that angle, the field's going that way, it accelerates that way. Well, if I let it go for a little bit, it's not going off at that angle anymore because it started going backwards. So it's moving, which means the acceleration is going to be, because the acceleration has to stay perpendicular to the velocity. So as the velocity starts changing direction, the acceleration is going to be changing direction too. And it seems really, really complicated, doesn't it? But we've actually seen this scenario in the first semester. So what type of motion do we have where the velocity and the acceleration are always perpendicular to each other? Do you remember a scenario where velocity and acceleration are perpendicular to each other? No. Okay, so going back to first semester. If you have motion in a circle,
See, I was going to say that, but I thought it sounded way too simple.
so we had good old centripetal force, which centripetal force is, I mean, I want to say it's not a real force. It's not a force like gravity or whatever, where there's something specific that causes there to be a force. Centripetal force is just, what? Yeah, it's any force that makes you move in a circle is centripetal force. So basically, if for some reason this could be gravity pulling the moon around the Earth. This could be a rope tied to something and you're swinging it around yourself. Whatever it is, you've got some sort of force that keeps you from flying out and you're swinging around at a constant v, then that's centripetal force. Okay. And the v is always tangent to the circle. The force is always towards the center of the circle. So sure enough, the force is always perpendicular to v. And what about the size of the force? Well, last semester we got that in order to keep this thing going, you have to have that the force is mv over r, or sorry, mv squared over r. R is the radius of the circle. So let's start out, let's do a couple more things and then we'll actually jump to the homework. So if we have a particle with velocity v, mass m, and just for the grins of it, we'll say it's initially, it moves perpendicular to the field. Question is, what happens? Well, we already said it's going to accelerate perpendicular to the movement and perpendicular to the field. But as it accelerates, the velocity is going to start changing direction and all that crap, and it just gets complicated. Well, what happens? It just goes in a circle. So here's the magnetic field. All it's going to do is it's just going to go in a circle around the field. And so, well, we kind of know where the center of the circle is because it's going around the magnetic field. So the only thing we really want to know is, hey, what's the radius of it? Well, we can get that just by going back to our centripetal force formula. On one hand, this magnetic field is making a centripetal force. So that force has to be mv squared over r. On the other hand, it's a magnetic field. So it has to be qvb sine theta. Right. And we said that v is perpendicular to b, so that theta is 90. What's sine of 90? Hope we held up the right number of fingers if you didn't say it. Yeah, sine of 90 is 1, so that's just 1. So we get the r, if you just get that by itself, qb over mv. So if you put a particle in a magnetic field and you start the particle moving perpendicular to the field, it's just going to go around in circles. And you can find the radius in terms of the mass, velocity, and the charge and the size of the field. So, all right. Now let me ask you, okay, so that was if I have a field and I start off moving perpendicular like that. What if I have a field and I put the guy moving in the same direction as the field? What's the field going to do to it? So this one we says goes in circle, round field. But what if I start off with the velocity in the same direction as the field? What's going to happen? So remember, the formula is V cross B times Q. So that's QVB sine theta. What's the angle between my V and my B? is zero. What sign of zero? Is zero, right? So zero. So the force on this particle from the magnetic field is zero. I mean, so it's just going to keep going in a straight line. I mean, it's like the field's not even there. So in this case, the field does nothing. And then if you go kind of in the intermediate case, I'm going off at an angle like this. Well, back to beginning of physics, the first thing we learned is if we don't understand something, we split it into parts that we do understand, right? So you think, okay, well, this vector, I can think of it as being a horizontal part and a vertical part. The horizontal part is completely unaffected. The vertical part wants to go in circles. So what's it going to do? Well, the horizontal part's not going to do anything. But it's going in circles. That means the particle's just going to run loops forever around the magnetic field. So that's the moral of the story. Let me write down the moral of the story. So if we had electric fields and we put in charged particles, the particle follows the field. Or it goes against it if it's a negative charged particle. But yeah, basically the particles are following the field. For a magnetic field, kind of all things being equal, the particle wants to go in circles around the field. I should probably say field lines rather than fields, but yeah. So electric fields, I mean, you draw your field lines, the particle follows the field lines. Magnetic field, you draw your field lines, the particle goes in circles around the field lines. So it's kind of weird.